In this pre-lecture video, we're going to be discussing Newton's laws. Specifically, we'll be talking about Newton's first and second laws. So Newton's first law is sometimes referred to as an object in motion stays in motion, an object at rest stays at rest. But more specifically, it is stated that if there is no net, where when we say net, we mean total, so no total external force that's acting on an object. So if there's no net external force on an object, then the object won't accelerate. And if an object is not accelerating, right, then we know that that means it has a constant velocity, where velocity is a vector. So even if something's moving in circular motion, remember that it is accelerating, even if its speed is constant. So the velocity is speed and direction, and that will stay constant unless there's a net external force acting. Now, related to Newton's first law is the idea of mass and inertia. So we haven't yet talked about or defined mass in this course. So mass is a measure, so it's the measure of an object's linear, and I'll put linear because eventually we do rotation, so it's a measure of an object's linear inertia. And so what inertia is really just an object's desire to follow Newton's first law. It wants to keep a constant velocity. So inertia is the resistance to a change in velocity. So if you're driving in a car and you're going at a constant velocity, and then you hit the brakes, your body wants to keep moving with that same velocity, even though the car is stopping. And so you feel that inertia. You feel that your body wants to continue with that same velocity. So there's a lot of times where you can experience inertia, and mass is a measure of an object's inertia. Now, it's important to note, and we'll talk more about this during class, that inertia is not a force. Sometimes it can feel like a force. For example, with the car and you hit the brakes, you feel like you're getting forced forward, but you're not. That's just you obeying Newton's first law. So it is not in itself a force. So that's really all that we're going to talk about in terms of Newton's first law. And related to problem solving, Newton's second law is really where all of the important stuff happens. So Newton's second law is going to be used throughout this course in various problem solving methods. So we have to have a really good understanding of the basics. So in equation form, we can say that Newton's second law is that the sum of all forces, and force is a vector, is equal to the mass of an object times the acceleration of an object. So in words, the left-hand side of Newton's second law is that the sum of all individual forces acting on a mass. And this, in this case, would be a mass m. So this is a mass m, an object has a mass m, and this would be what we call the net force, which is specifically the sum of all the individual forces acting on that mass, only on that mass. And then that's going to then be equal to the mass of the object times the acceleration of that object. So acceleration of mass m. Now in problem solving, sometimes we have multiple dimensions, and so we can write this in components. And so we can write this out and use it in component form, where the net force, the sum of forces in the x direction, is equal to the mass times the acceleration in the x direction. and the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So this is how it shows up in problem solving, as we'll see. Now we're talking about forces now, and so if we look at this equation for Newton's second law, we can see that the unit of force is going to be equal to mass times acceleration, so it'd be equal to kilograms times meters per second squared, and that's what we define as a Newton, which is used as a capital N. And see how you can look at the equation in order to figure that out. Now, because this left-hand side is the sum of all individual forces acting on a mass, we need to talk about how to find those individual forces. You observe the net force by looking at the acceleration and multiplying by the mass, but the individual forces are sometimes hidden. For example, right now I'm sitting in my chair and I have a downward force of gravity on me, and I have an upward force from the chair on me. So I have two individual forces acting on me, and they add to 0, which is why my acceleration is 0. So what I'm going to do is give a list of all individual forces that we're going to use in this class. So we can say here, a list of individual forces that we will use in UP1. Now there are more. Next semester you'll have magnetic forces and electric forces, but in this semester we will actually only have 5 different forces that you will use when you're trying to identify the net force on an object. So these individual forces, to make a list, the first one is going to be the force of gravity. Now note that force and acceleration are not the same thing. They're related through the mass. So force of gravity is not the same as acceleration due to gravity. Force of gravity is defined as also the weight of an object. So when we see weight, it's not the same as mass. Weight is going to be equal to a force. So the force of gravity is basically the force on something due to gravity. And so if we take the positive j hat or y component to be up, then we know that the force of gravity is going to be equal to negative mg j hat, meaning that the force of gravity is downward. Remember that g is always a positive number, so 9.8 meters per second squared, if we're near the surface of the Earth. So the force of gravity is downward, and it's equal to the mass times g. It is not the same as g because it's related to the mass. So something that's heavier has a larger force of gravity, which has a larger weight, as we'd expect. The other type of individual force, I'll just call a push or a pull. Now, this is really, pretty obvious in a problem because the problem will say somebody's pushing on a box or they're pulling on a rope. And so really this will be given or stated in the problem. The tension is another type of force. Now, often if there's a rope or a wire, then we're going to have a force of tension. So the tension is going to be a force from a wire or a rope, etc. And a main thing to think about when you imagine pulling on something with a rope, that the rope always pulls on an object. Tension always points away from the object along the rope. So tension always points away from the object along the rope, just as we'd expect. So when we do work with what's called free body diagrams, which I'll talk about shortly, then just keep this rule in mind about tension. So for example, if I have, say, 2 blocks and they're connected by a rope, and then I'm pulling on the first block with some force F. This would be, say, a push or a pull, in this case, a pull. Then the tension in the rope, if I look at this object, the tension in the rope would point away from the object along the rope. And then on the front box, if you imagine what that rope's doing, it's again acting along the rope, but in this case, again, away from the object, so it's pointing in a different direction for that particular object. The other thing for us to note with tension is because we're ignoring pulleys, then if we have a pulley and it's, say, on a table, and then there's a box on the table and then a rope hanging over the pulley and another box hanging from that. Well, we're ignoring for now the pulleys. When we get to rotation, this will change, but the tension is going to be equal in magnitude all points along a rope. So here we can say that the tension is equal at all points. For one rope, for one continuous rope, the tension, the magnitude of the tension is the same at all points. All right, so that's 3 of our things. We have force of gravity, push or pull, and tension. Another force, the 4th force, is friction. Now, friction actually gets its own video, which you'll watch shortly. And so I won't talk much about friction now, but that's our 4th force that's allowed. And then the last one is what we call the normal force. So again, force of gravity, push or pull, tension, friction, and normal force. You can use these as a checklist as you do problems involving Newton's laws. The normal force, the normal comes from mathematical term for normal, meaning orthogonal, which means perpendicular. So this is a perpendicular force. This is a contact force between 2 surfaces that is always perpendicular to the surfaces in contact. And we use N. I use little n, some people use capital N. And so these are all choices, capital N or F sub N. All of these can be used for normal force, and that's what we then will use when we're drawing diagrams. Now, a couple notes about the normal force. One of them is that because it's perpendicular to the surface, then we can look to see what would happen, for example, if we have a block on a ramp. A block on a ramp, then the force of gravity, say, would point straight down towards the center of the earth. But the normal force is going to be perpendicular to the surfaces in contact. And so the normal force points perpendicular to the ramp. And then the scale, the other thing that shows up in problem solvings, problems, is going to be that a scale, if you have a problem saying what does the scale read, a scale reads what you feel pushing up on you. So a scale reads the normal force. So a scale reads the contact force between 2 surfaces. So if you push harder, if I had a scale on this table and I push harder down on it, then it's going to read more than my weight. So a scale will read the normal force. So keep that in mind as you go through problems as well. Okay, so for the last part of this video, then we're going to talk about how to draw free body diagrams. The very first step in any problem involving Newton's laws is always what we call a free body diagram. So free body diagrams, when we apply to Newton's second law, the sum of individual forces, remember, is going to be equal to the mass times the acceleration. Well, we need to isolate. You need to isolate the object. So isolate the mass m, meaning that you're going to separate it from its surroundings. So let's say, for example, I have, a box on a ramp. Then in that case, I might draw not so much the ramp, but I can just draw the box of mass M. Or if it's a box in an elevator, I might not tilt the box and I might just have, say, a box of mass M like this. But I'm just isolating my object. I'm removing it from the rest of the picture. That's the first step. Then, because I want to isolate these individual forces, I want to draw the individual forces that we just came up with. We want to see our list, right? That we just made a list of ones that are allowed. We want to draw our individual forces acting on that one object, on that one mass M, not on anything else happening. You're just imagining, what if you are that mass? What forces are acting directly on you? And to do that, you're going to draw arrows pointing in the correct directions. And when possible, you want to draw these to the correct relative scale. So for an example, for the box on the ramp, I might have my object here, and then I'm going to have a downward force of gravity, which you can write as F sub g. You can also write that as mg. And then you're going to have a normal force. If there was friction, I would also add that in and it would act parallel to the ramp, but we're not doing friction yet. So that might be what my free body diagram looks like for a box on a ramp at this part. If it was a box that's just, say, in an elevator, sitting on the floor of an elevator, then I might have a downward force F sub g, which again equals mg, and then say an upward force from the contact between the ground and the box. So I'm going to draw those individual forces. Now, there's a couple important notes here. You're never going to put acceleration as a force. Acceleration is not a force. And you're never going to put ma, which is the result of a net force, but not a force itself. So never put ma as a force either. Neither of these belong on the diagram. Only use forces from the list. So that's our basic free body diagram, but to make it useful for problem solving, there's two more steps. The next step is going to be to identify if the acceleration equals 0 or not. And then label the acceleration as a double arrow near but not on the diagram. So if I go back to these diagrams here, then let's say that this block was sliding down the ramp, which is exactly what would happen if there was no friction. Then near, but not on the diagram, I'm going to draw that downward arrow, and that would be my acceleration. If my acceleration is 0, I would just write a equals 0 instead of drawing the double arrow. Here, let's say my normal force is less than my weight. And we'll see in situations when that could happen. Then I would have an acceleration that would be downward. So my acceleration would point down. So I'm adding that to my diagram. And again, this is exceptionally useful for problem solving. The next and last thing for a free body diagram is to put an axis near but not on the diagram. And so when we're doing problems, we have to know what we're defining as x and y axes. And so if I have the block on the ramp, an interesting thing is that I can tilt these axes. I'm allowed to tilt the axes. So I would go to this one, and then I would maybe say, okay, I'm always going to want to take one of my axes so that my acceleration is 0 along that direction, so perpendicular to the ramp. So I would maybe call this my x and my y axis. You can choose whatever you want in terms of whether you call positive x to be down the ramp or up the ramp, but I just choose a right-hand coordinate system. And so this then would be my completed free body diagram, where I have drawn the individual forces, identified my acceleration near but not on, and made an axis near but not on. For the elevator case, there's no need to tilt my axes, and I only have a single direction. I don't worry about the x direction at all, so it's just a matter of what I'm calling positive y. So it might look something like this, and that would then be my completed free body diagram for the box in the elevator. All right, so that concludes this pre-lecture video, and we'll continue this information in class.